So for lesson 6.6, we are going to look at the two types of sequences that we've been working with, which are both geometric and arithmetic. And we're going to look at them from a slightly different point of view and explore a different equation that helps us define or describe the sequences similarly to the way that the explicit equation or the explicit formula did. This one's just a different version. So we're still talking about sequences, and in this case, we're looking at the recursive. So let's talk for just a moment. What does it mean when we say recursive? So this is actually really simple, and it can look a little intimidating, but try to not overcomplicate it because really it's a pretty simple concept. So a recursively defined sequence is a sequence that just describes what the pattern is. Fibonacci sequence is a recursively defined sequence. It basically is saying, hey, I'm doing this to each previous number to get the next number in the sequence. So if we look at the arithmetic sequence, for example, we know that it has the type of pattern where you're multiplying a common difference every time. You're adding you're adding a common difference every time. So we played around with those on the previous lesson, and the explicit formula allowed us to kind of get ahead and jump ahead to any other term or nth term. Okay, now let's look at how this recursive arithmetic sequence looks different. Okay, so all it does, it's really just very basic. All the recursive says is, hey, each new term in the sequence is the previous term plus the common difference. Okay. So honestly, you've been doing recursive, at least in your head or in your conversations, already. Because when we describe the pattern, when we see, so just to give you a little example, let's say I've got this right here. And I say, hey guys, what do you think is going on there? And you say, oh, they're adding 3 to every term to get the next term. That's it. You just defined it recursively. That's exactly what you did. You just basically told me, so let me give you the answer to this right here, right? You basically told me, oh, every new term is just the term right before it plus 3. That's it. That's your recursive for that arithmetic right there. So it's really just an algebraic or symbolic description of what the pattern is versus the one that we played around with in the previous unit, the explicit. That one allows you to kind of jump ahead and find, the 150th term if you wanted, right? That's not going to help you with this one. This one's really just giving you a symbolic or algebraic explanation of what you're doing to each of the previous terms to get that new term, right? So we're just saying, hey, every new term here is going to be the previous term plus 3. That would be a recursive equation for that arithmetic sequence. And very similarly, for the geometric sequences, it's going to be the same idea. Okay, so the recursive here for the geometric is simply going to state that every new term in the sequence is equal to some common ratio times the previous term. Okay, times the previous term. And so that's kind of those letters ran together. Let's do that again. Okay. And so when you see that n minus 1, that's basically the term right before this next term, right? So in other words, if n was 3, n minus 1 would be 2. It'd be like, oh, if you want to find the third term, you take the second term, and you multiply that by that common ratio. All right. So, just like we did before, if we had started with a number, like, let's keep it simple, 2, and then I notice the next one is 6, and then I notice the next one is 18, and so forth, so forth. I'm looking at, and I'm like, oh, I see that they're multiplying by 3. That's all you need to know. You would basically, what you would have described verbally to me and would say, oh, the pattern is they're taking each previous number and multiplying it by 3, Miss Sherida. Then I would be like, okay, so every new term in the sequence is 3 times whatever the previous term was. That would be it. That would be your recursive for that geometric. It really is that simple. So it looks a little wonky, especially with the little n-1. That really just means previous term. And it's really just an equation or an algebraic expression that describes the pattern. It's only really helpful to extend to the very next value. So if all you're doing, it's what you use every time that you extended the sequence. Every time that they said, please find the next 3 terms, and you just applied that pattern, you were doing that recursively. Okay? And then, so if you want to know what's the very next term, that's what you do. You use the recursive. When you want to jump over and find that 70th term, then you use the explicit, right? So let's take a look. Let's just kind of practice reading it, okay? So if you look at number 1 here, after on the first table here, we want to write the first 6 terms of the sequence and then graph it, right? So let's kind of dissect what it's giving us here. It's telling us here that the very first term in our sequence is -2. We usually say, hey, this is where we're going to start. And then this part is telling us that every new term after that is just going to be -2 times that term right before it. Okay, that's what it's going to do every time. So if in that first slot, okay, we're not going to have to do any work here. Okay, the first term in the sequence is -2. There it is. But then to find the second term in the sequence, according to this recursive right here, every new term is going to be -2 times the term right before it. So it's going to be, to find this second term, it's going to be -2 times this term right before it, which is also -2. So then this comes out to 4. Okay? And then to find the third term, according to my recursive, I'll just do -2 times that previous term of 4, right? And -2 times 4 is -8. So it's just extending the pattern. That's all it is. It's just an algebraic way of describing what that pattern is doing. That's the big idea. Okay? And so if we just keep this going, for the fourth term, it would be -2 times that previous -8. That would give us 16. And then just to finish it out here, -2 times 16 would then be -32. And -2 times -32 would land us at a positive 64. Okay? And then we would graph those. So we're going to have to get creative here with this axis. We do have positives and negatives. So I might do something like, give myself a little bit more room here. And I'm going to have to, let's see, I got to get all the way to 64. So maybe we'll go up by 20s here. Let's see. So maybe this is 20, 40, 60, 8. Okay, that'll work. And -20 and -40. I think we should be okay there. All right, so the first term in the sequence starts at -2. Obviously super tiny point, right about right there. We're going to just estimate that out. The second point in our sequence was a +4. So almost just as tiny, but on the positive side. Then we have the -8. That starts to give us a little bit more room here, away from 0. And then the next one is a 16. So now we're talking, this would be about 10. So 16 would be up here a little closer to 20. And then -32 would get about, that would be 30, would be about right there. And then the last one, numbers would be 64, which would probably be somewhere right in here. Okay, so there would be our graph. But the primary, the primary concept here is just using the recursive and understanding that it's a really not as intimidating as you might think or as it might look. It's really just a matter of, let me switch this down, finding the pattern and using the pattern. That's what the recursive is all about. So if we look at number 2, first of all, I didn't really emphasize this, I assumed it, but I want you to look at that and be able to recognize, oh, this is geometric. This has the characteristics of a geometric because every new term, it's going to be a number times the previous, right? So this is geometric in nature. We should have kind of had that conversation. And so according to them, I'm starting at 4. And then according to the recursive explanation I have up here, every new term is going to be 1.5 times the previous. So this new term, number 2, is going to be 1.5 times the previous term. Okay, so when I do that, that's going to come out to 6. So the second term is 6. Okay, and then the new term after that will be 1.5 times that previous number, 6. And when I do that, I'll get 9. And then we just keep going, right? So it's just the recursive. It's just saying, hey, what are you going to do to the previous term to get that very next term? So when I do that, I get 13.5. I should have been writing those on that side. And then 1.5 times that 13.5 will give me the next term in the sequence. That's going to be 20.25. And last but not least, 1.5 times that previous term is then going to give me the next value in the sequence. This one's going to be 30.375, I believe. And then we would graph those. Again, just comparing position compared to the actual value. Okay, so if we go to graph this one, these are all positive, so I don't have to worry about having the negative quadrants on here. And go right here to the first quadrant. And I'm going to have the first, second, third, fourth, fifth, and sixth terms is what we're graphing. And I need to get all the way to 30, so 2, 6, 7, 8. Oh, not quite. Okay, so maybe I'll go by 4s here. So let's go by 4, 8, 12, 16, 20, 24, 28, and 32. Oh, that's a pretty good fit. All right, so let's go through it. So the first term in the sequence was 4. The second term in the sequence was a 6. The third term in the sequence is a 9. We're looking about right there. The fourth was a 13.5, which is right about right there. And then the fifth term is right about 20. And the last one was just at about 30, which would be about right here. So that would be our graph for the sequence. And it's okay to estimate them as long as they make logical sense. Okay, so we're going to leave the... Oh, no, these are arithmetic, of course. We're going to do these, or at least one of these. Let's do that. Okay, so how did I know that was arithmetic? Because I'm looking at that recursive, and it's explaining to me what the pattern is going to be. So according to number 3, the first term is 14. And every new term, let's review, right? Every new term in the sequence is going to be the previous term minus 4, or plus a negative 4, however you want to think of that. It's the same idea, okay? But it's decreasing by 4 every time. That's all that really needed to tell me. I'm ready to go. So the first term is a 14, so we're okay there. For the second term, I would take that previous term and do minus 4. And that would give us 10. So the second term in this sequence would be a 10. And then to find the next term, it would be the previous term minus 4. That would land us at a 6. And then to find the next term in the sequence, I would take 6, subtract 4 again. We'd get a 2, and you get the idea here. And then we'll finish it out here. We'll take that 2, subtract 4. That'll give us the next term in the sequence. There you go. And then last but not least, we'll take that previous term, subtract the 4, and our very last term that we're going to actually have on here is negative 6. Okay? And then we would graph that if they ask us to. Looks like I do have some positives and some negatives. Of course, the number of terms is going to stay positive. I mean, yeah, number of terms is going to stay positive, but I'm going to have some negative value, so I'm going to go like this, and what do I want to go by here on the y-axis? I need to get from 14. 1, 2, 3, 4, 5. Maybe I'll go by 5, 10. Let's go by 3s. So 3, 6, 9, 12, 15. That should fit. And then negative 3. Negative 6. Okay, so the first term in this sequence was 14, so be about right there. Okay, second term was a 10, be about right there. The third term was right at 6. There's that. Fourth term was at 2. Fifth term was at a -2. And the sixth term was right at -6. Okay, and that would be our graph for that sequence. So that's really the main idea. Let's go ahead and move on to writing recursives for tables and lists or sequence lists. And let's start with number 5. So here it says write a recursive rule for the sequence. So we have a table. First, we got to figure out if this is going to be geometric or arithmetic. Okay, based on the way that I see that decreasing, I'm pretty sure that's going to be geometric, but we can test that with a calculator, right? We can look at that and, you know, see if 108 divided by 324 gives us the same thing as 36 divided by 108, or 12 divided by 36, and indeed, every one of those comes out to a third. So I know they're multiplying by 1/3 here. And you can do that on the calculator and confirm it if you don't believe me. But really, if I was just saying what I just said, oh, every time they're multiplying by a third, that's it. I just gave you the recursive, right? We're just going to write that algebraically. So for this one, we're going to say, since it's geometric, we're going to use this template. We're going to say every new term is some common ratio times the term right before it. That's it, right? And so since our common ratio is 1/3, then that's really all we need to insert here. Okay, our recursive rule here would be that every new term is equal to 1/3 the previous term. That's it. And then it's always really helpful to also know where you began. So we'll say this is the rule, right? We'll say that, and we'll say, and we started it at 324. And that right there is all the information. It's just really a description of what's happening. Okay, that would be your answer. Okay. Let's try it on number 6. On number 6, if I try those ratios, I don't think they're going to work, but if I look at differences, looks like this is increasing by 5 every time, because when I do 14 minus 9, I get 5. Okay, 19 minus 14, I still get a positive 5. 24 minus 19, I still get a positive 5. So this is arithmetic, which means that the recursive would be something along these lines. Every new term would be the previous term plus that common difference. Okay, and in this case, we would just need the common difference. And now that I know that, oh, the common difference is a positive 5, the recursive here is every new term is just the term right before it plus 5. That defines the pattern. And then it's always good to say, and we started it at 9. That was the first term. So as long as you know the first term and the pattern, that's all this is giving you, is that basic information about the sequence. Okay? And you should be able to do that whether it's in a table or just as a list, as long as you can identify the first term and either R the common ratio or D the common difference, you can write the recursive. Okay, it's actually simpler than what we were doing before. Okay, so check this one out. I'm looking at this. Obviously, the differences are not the same, so I would look for common ratios here. So here, my first term is going to be 3,125. And by dividing new by previous, new by previous, new by previous, by doing that division, I quickly realize that R is 1/5. That's my multiplier. Okay? And as long as I have those two ingredients, we can bake this cake. Okay? Because I can just say, oh, okay, the first term is 3,125, and then every new term after that is just going to be 1/5 times the term right before it. That's your answer. Yes, folks, it is that easy. Okay? This guy, I see a flip-flopping sign. I definitely know that's going to be geometric. And all I have to do is divide new by previous, new by previous, new by previous. I can figure out here that my R is a -3. My first term in this sequence was an 8. That is the only thing I needed to know. I can write this recursive. All I have to do is tell my viewers or my listeners, hey, we started at 8, and every new term is going to equal -3 times whatever came right before it. Okay, that's it. It is that easy, folks. Good. All right. Let's try this last one, number 9. If I try ratios here, I don't think they're going to work. But when I look for a difference and I subtract new by previous, new by previous, new by previous, I realize there's a common difference here of 6. And the first term was 7. Okay, so as long as I know I started at 7 and that this is adding 6 every time, I'm just going to then describe that with my recursive. I say, hey, we started at 7, and every new term in this sequence is just the term right before it plus 6. That's our answer. Okay. All right, so hopefully that's feeling pretty comfortable there. You could even do it from a graph, so we'll do one more from a graph. The graph really isn't any different. It's just representing the sequence in a different way. Just like on the previous page here, or previous, we had a table, we had a sequence list, or a graph. It's really giving you the same information. And if you like the list better, feel free to take this graph and rewrite it as a sequence, because that's all this is telling me. All this is telling me is that the first term in this sequence was 15, that the second term in this sequence was 12, that the third term in this sequence was 9, and that the fourth was 6, and then the fifth was 3. So this graph is just telling me that the first term, you know, the x is telling me what term it was, the y is telling me the actual sequence value. So it's just kind of the reverse of the graphing we were doing on the front. Now we're just going in the other direction. And again, you don't have to do what I just did. It's just that if you see patterns more easily, if it helps you to see it listed out, then do that, right? Look at it like this, and that might let you kind of subtract that new by previous a little bit more successfully, then go for it. So in this particular case, I can tell my first term is at 15. That was my a sub 1, my first term. And that there's a common difference here of negative 3. Right? 12 minus 15, 9 minus 12, 6 minus 9, those all give me negative 3. So it's a common difference of that negative 3. And once I know that, I can write my recursive. I can say, okay, we started the sequence at 15, and every new term in the sequence is simply the term right before plus a negative 3, or you could even just write minus 3. You know, that's how I'm going to roll. I don't like those double signs, but both of them are technically correct. All right, so if we feel good about those, then let's finish out with probably what's a little bit more complex here, which is kind of swapping back and forth between explicit and recursive. Okay, this might be the one place where you might have to be a little bit more awake. So on 18 through 14, we want to write an explicit rule for the recursive. Okay, so now we want to write an explicit. So now we're writing the ones that we started with, right? Based on the recursive. So remember, for the explicit, that I still only just need the first term and either D or R, and I'm still okay. So I'm going to look at number 12, and the first thing I need to do is look at this recursive and decide if it's geometric or arithmetic. So based on this information right here, I can tell this one is geometric. Okay, because it's multiplying by 3 every time. That's the pattern. Okay? And if it's geometric, then all I need is this first term, and to identify that R is 3. Okay, so with this information right here, I can now rewrite that original recursive information in the explicit that we had learned originally, which looked like that, just to refresh our memory. Okay, this is the one that really allows us to get ahead and jump out and say, hey, I want to know the 85th term. And so then you can use this one, because you wouldn't want to, the recursive really wouldn't help you with that. The recursive just describes a pattern, and it lets you find the very next consecutive value. If you want further down the line, you really need this guy, the explicit. Okay, so as long as I still know the first term and the R, though, I can still write this. So here, it would be a of n, or a sub n here, equals, and then I would insert my first number, open a parentheses, insert my common ratio, raise it to the n minus 1, and that is the explicit rule for that recursive equation. Okay, so let's try it on number 13. First of all, look at that recursive and determine if it's arithmetic, or geometric. So if they're telling me here in that recursive that every new value is equal to the previous one plus 11, that tells me that this is arithmetic. Okay, and that tells me that I need the first term and the common difference. Well, the common difference is looking at me right there. Okay, it's at 11. So with this info, I can then write the explicit for the arithmetics, which looks like this, because I like to put the D in front of the parentheses. Okay, it just says, hey, you can find any term now, because you know that any term in the sequence can be found as long as you started with 6 and you do 11 times whatever n minus 1 is. Now on this one, just don't forget, this is lovely and it is correct, but we do then take it one step further and we simplify it. So once I've set up this explicit arithmetic rule, I will distribute the 11. So that'll be 11n and negative 11. And then there'll always be two constants that are like terms there. In this case, it is the 6 and the negative 11. Those are like terms that will combine. So I'll end up with 11n minus 5. And that is the explicit rule for that recursive arithmetic. Okay. Try the next one on your own. Press pause, give it a shot, and then come back and check it. And if you did that, hopefully you determined that this one was geometric because they're multiplying by 5 here in the recursive explanation. Okay, so that means that R is going to be 5. And then I would, oh, I just cut that off like that. So this is the information that I need to know. The first term is negative 1, and my common ratio is 5. And I can use that to write this explicit by just filling in the first term, which happens to be a negative 1, and the R value. That's it. There is our explicit formula for that geometric function. Okay. Then let's talk about just going in the opposite direction. What if we start, we want to write a recursive from an explicit rule? It's still the same idea, guys. As long as you know what the first term is and what the common difference or ratio is, then you're good to go. So let's try 15. Okay. So on number 15, we need to know, first of all, what is the common difference. The way that this looks, it's definitely going to be arithmetic. And I want you to notice one thing. This we may not have emphasized it because we didn't really need to, but even in this simplified version right here on number 13, the number in front of n is still your d. So d is preserved. You've got that 11, it stays there. Okay, so when I see this 6 right here, this tells me that that's my common difference. My common difference here is 6. Okay, and then the only other thing I need is what is the first term in this sequence? Well, that's what recursive is all about, right? So all I have to do, yeah, that's what explicit is all about. Sorry, I'm about to write the recursive. So if I want to know what is the first term in the sequence, all I do is plug in a 1 and say what is 6 times 1 plus 2, right? Because I want the first term. So 6 times 1 is 6, plus 2 is 8. That would be the first term in this sequence. So I know that the first term in my sequence is 8, and I know that every new term is going to simply be the previous term plus 6. Okay, there's my first term, there's my common difference. This would be the recursive explanation for the pattern. Okay, let's try the same thing on number 16. Yeah, 16. On number 16, we know that R is always sitting right here. So we can tell here that R, or the common ratio, is going to be negative 3. The other ingredient I'm going to need is the first term. So I'll just evaluate my explicit for when n is equal to 1. So if I solve this equation and I insert a 1 for n, let's find out what that is. Well, what's 1 minus 1? It's 0. And anything to the 0 power is just 1. So my a sub 1, or my first term in this sequence, happens to be 1. Once I have those two ingredients, I can write my recursive. All I'm going to do is describe this pattern. I'm going to say, hey, we started at 1, and every new term in this sequence is simply negative 3 times the term right before it. And there's my recursive description or explanation. Okay? Alrighty, let's finish out with one or two of these. Writing the recursive. These are, actually, you know what? I just realized which ones these are. These are the ones that I wanted to do in class with you guys. So this concludes the lesson video. When you get here into class, these are the ones that I want us to do together. You can certainly give them a try. They're kind of fun. These are, I'll tell you right now, not geometric and not arithmetic. They have other patterns. But that's kind of the nice thing about recursive. As long as you can tell what the pattern is, you can write the recursive formula. That's all the recursive is. It's just a description of the pattern. So like we could have written a recursive for the Fibonacci on that first day that we talked about it, right? As long as you can describe, oh, they're adding, you know, the first term and the second term and multiplying by 2. But then, boom, there's your recursive, right? It's just an explanation of the pattern. There it is. So we'll do those in class.